Uh, Good afternoon, everyone. I'm sorry to split the room, but water crisis is a real challenge to human existence. So we should be naturally worrying about this problem. This is a movie from New York Times reporting on the declining water level in the United States in the last 80 years or so. And on the top, you have a timestamp that's actually increasing, and the red and orange dots on this map that represents the declining water level, especially the groundwater level, which is really alarming that how the Midwest regions are actually, the water is actually dropping in those regions. But if you look at the entire world, the problem is even more worse. As we speak, there are 90 countries based off Middle East, Africa, and Asia are seriously endangered or plagued by this problem because of the climate change and all the other issues. And in fact, there are 90 countries who are either insecure or critically insecure by this problem. Now, we still have 70% of the water, right? So we should be able to convert that into drinkable form of water. But there is a problem, and that is 97% of the total water resources on Earth are in the form of salt water coming from the oceans. And it is very hard to drink that. So you need to convert that water into drinkable form of water. And that's part of the challenge. But luckily, there have been a booming of filtration technologies. Countries are taking large-scale water desalination projects seriously. Terms like RO purifying water is becoming a daily household term, where RO stands from the reverse osmosis. And so people are really investing a lot of effort into this business. And as we speak, there are also other technologies such as Nano-Filtration, which also relies on the similar principle of size exclusion, where your filter has certain pore which have some critical dimensions or cutoff radius, and the particles which are bigger in size will be rejected, and the particles which are smaller in size than the pore dimensions will actually be able to pass through the membrane, and that's how you can get a clear water resource. Now, I'd like to dig deeper and try to understand this problem at a molecular scale. And for that, I'd like to start with a grain of salt. We all have done that at our house, is to take a tablespoon of salt and mix it in water. And you have seen how fast this process is. And that's mostly because the salt, which is basically a composite of salts, composite of positive and negatively charged ions, and the moment you add water in it, it dissolves everything. And in this process, there is a water layer around the ions that really stabilizes them. And this process is so energetically downhill that, in fact, doing the reverse is very, very hard. That is to separate the salts from the water. Now, fortunately, the membrane can do that job, where the approaching ions and solvated waters can come in, and the water molecules can pass through the membranes, while the ions can be either rejected by the membranes or can be trapped in the membrane. But this is just a schematic. The actual process might be much more complicated, and in fact, we need to look at real time. So that's why I'd like to start with a video, and this is an actual simulation of an ion that is moving through the membrane pores. And you can see that the transparent part in this are basically the water channels through which the ion, which is a big dot at the center, is moving. And then the opaque parts of the membrane. You can see how complicated the dance is, right? Yet it is really exotic. The ions is moving through it along with the water molecules. And in this dance, there are three major players, which are the membranes, the waters, and the ions, which are constantly switching partners in this process. So the question that we have to ask is, how fast do these ions move through the membrane along with the water molecules? So once we have this information, then what? How does that actually reflect on the large-scale applications, which is to separate salt from the water? So the point I'm trying to make is that we have the fundamental knowledge, what's happening at the microscopic picture that we are trying to understand, and then on the other hand, we have the macroscopic picture, which is to separate the salt out of water. And trying to bridge the gap between these two ends is one of the purposes of this project, which is to go beyond trial and error approach in order to make a better filter for the next generation devices. Now, coming back to the question of how to track the motion of an ion. Well, for that, I'd like to start with an analogy where I am the ion, for instance, and you guys are the observer, and you want to track me down as a function of time. Now I would like to go to a roller coaster, and I'll start a journey. Okay, I start the journey. It's a bumpy ride, and suddenly you are interested how I'm doing through this ride. And for that, you ask me to wear an Apple Watch, through which you can extract all the data that you need to understand my behavior or my motion or my journey, my experience through these motions. That will do it, right? Now, how to do that for the ions? Or in other words, what is that Apple Watch for the ions? So for that part, we need to rely on the lasers, which are very tiny in time, so tiny and precise that they can work like a clock to track these ionic motions, which are also tiny in time. And with this method, you can answer questions like, how fast does it take for the ions to come off from the surface of the membrane to actually go into the water channel? And if you measure this process, it turns out to be 0.5 billionth of a second. So that's how short it is. That's how tiny motions that they are going through that we are actually tracking down here. And finally, how do you do with this kind of information, right? So for that, I'd like to go to the question that I started with, what can make you a better filter? An ideal filter would always slow down the ions as compared to the water molecules while they are having their ride through the membrane channels. So I start on the left with the ion that is solvated by the water molecules, and that has to go through the membrane. And if the ion, which is A here, interacts more frequently or more strongly with the membrane wall as compared to the water molecules, then you have a chance to separate the water molecules as compared to the ions by slowing them down. And that's sort of the purpose or a big picture here is how to make them slower as a function of time. Finally, I'd like to borrow this phrase from Coleridge and really stress upon the fact that this is 21st century and we need to convert every drop of water that is out there into drinkable form of water. And it seems like from the projection of the water technologies or the market size of the water technologies for the next decades that we are heading into the right directions. With the ray of hope, I'd like to conclude my presentation here. You have been a great audience. Thank you.